Today we're going to continue our study in triangles by talking about perpendicular bisectors. Now as review, what is a bisector? Well, a bisector is going to intersect a segment at its midpoint. So when we're talking about perpendicular bisectors, this is a more specific type of bisector where any segment, ray, line, or plane is perpendicular to a segment at its midpoint. So there are two things here. It's the bisector because it intersects it at its midpoint, but not only that, it is also perpendicular to that segment at that point. So here's an example. So here we have line segment AB, and we have this line CP, and we would say that is a perpendicular bisector because at point P, not only is this line bisecting segment AB, so you can see how both AP and BP are equal to each other, but you can also see that CP forms a right angle with line segment AB, so we would call it a perpendicular bisector. All right, so we have a perpendicular bisector theorem, and this says that in a plane, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So here's a picture. So if a point is on the perpendicular bisector of a segment, so if point C is on that perpendicular bisector, then that point is equidistant from the endpoints of the segment. So CA and CB are equal to each other. Now the converse is also going to be true. So remember, the converse is if you switch the if and then statements. So if there is a point that is equidistant from the endpoints of a segment, then we could say it is on the perpendicular bisector of the segment. So here's an example. So say you have this point D, and you know it is the same distance away from A and B. If you know that, then you can say that D must also be on that perpendicular bisector of line CP. All right, take a look at example 1. Find AD if BD is the perpendicular bisector of AC. So we have this line, BD, and we're told it is the perpendicular bisector of AC. So that means AB and BC must be equal to each other. We also know, based on the theorem, that AD and CD must be equal to each other. Now you're asked to find the value of AD. So we want to involve AD in this. So AD is equal to CD by the perpendicular bisector theorem. Substituting, we have 5x equals 3x plus 14. And then solving, we have x is equal to 7. Now remember, you're not being asked to find x, you're being asked to find AD. Now AD is equal to 5x, so we can substitute 7 in for x, so that would be 5 times 7, which is 35. So AD is equal to 35. All right, example 2. WX is the perpendicular bisector of YZ. What segment lengths in the diagram are equal? Is V on WX? All right, let's start with the first part. What segment lengths in the diagram are equal? So you are told that WX is the perpendicular bisector of YZ. That means it cuts YZ in half. So that must mean that XY is equal to XZ. Now, not only do you know that, but you also know that because W is on the perpendicular bisector, you know that W to Y and W to Z, those will also be equal by the theorem. And then the diagram itself does tell us that Vy and Vz are equal to each other. So XY is equal to XZ, WY is equal to WZ, and Vy is equal to Vz. Now, the second part is V on WX. Well, since we know that Vy and Vz are equal to each other, they're both equal to 25, we can say, using the converse of the perpendicular bisector theorem, that V is in fact on the perpendicular bisector of YZ, which is WX. Okay, example 3. JK is the perpendicular bisector of NL. Mark congruent segments, find NK, and explain why M is on JK. So let's mark the segments that we know are congruent to each other. So we know that these two are equal to each other by the perpendicular bisector theorem, because we know K is on the perpendicular bisector, so K must be the same distance away from N as it is to L. We also know, because this is a perpendicular bisector, that from J to N and J to L, those distances are equal as well. And then lastly, we are told that LM and NM are both equal to 8. So those are congruent as well. So that takes care of part 1. Part 2, find NK. Now because we know that NK must be equal to LK, we can go ahead and write an equation. So we would say 6x minus 5 is equal to 4x plus 1. Then we can go ahead and solve and get that x is equal to 3. And now you're asked to find NK, so we're going to substitute 3 in for x in the expression for NK, which is 6x minus 5. So this would be 6 times 3 minus 5, which is equal to 13. Now the third part, why is M on JK? Well, you see here that M is the same distance away from L as it is from N. So, since we know that JK is the perpendicular bisector, we know that M must then be on the perpendicular bisector using the converse of the perpendicular bisector theorem. Okay, the next thing we're going to talk about is when you have multiple perpendicular bisectors in a triangle that are drawn. So the perpendicular bisectors of a triangle intersect at a point that is equidistant from the vertices of the triangle. So here's a picture for us. So remember, perpendicular bisectors of a triangle, we're talking about each side of the triangle has a perpendicular bisector, which are shown in blue in this diagram. So PD, PE, and PF are all perpendicular bisectors. So what this is telling us is that these perpendicular bisectors, these blue lines here, they intersect at a point, P in this case, that is equidistant from the vertices of the triangle. So this tells us that PA, PB, and PC are all equal to each other. So this point P, we have a specific name for this point where these perpendicular bisectors are concurrent, and we call that the circumcenter. So the point of concurrency of the three perpendicular bisectors is called the circumcenter of the triangle. So that circumcenter is equidistant from the three vertices, we just saw that. And the circumcenter is the center of a circle that passes through all three vertices. Now this we haven't seen yet, but we can take a look and see what we're talking about. So say here we have an acute triangle, and we have that point P where the three perpendicular bisectors are going to intersect. What this is saying is if you were to draw a circle that includes all the vertices of the triangle, the center of that circle would actually be the circumcenter. We can see it with a right triangle as well. So here's a right triangle. You can see those three red lines showing you the perpendicular bisectors, and you can then see where all three perpendicular bisectors intersect at point P, and that point P is the center of the circle that goes through the three vertices of the triangle. One more, we have an obtuse triangle, and in this case you can actually see that the circumcenter of this triangle is outside of the triangle, but the same thing still applies. So drawing all three of the perpendicular bisectors, getting the point of concurrency P, and drawing the circle that contains all three vertices of the triangle, point P is still the center of the triangle.